we're going to talk about how to take an integral, a definite integral. We're going to have the traditional integral rules. We're going to do it by converting this into a limit and a summation like we talked about last time. So just to give a quick reminder, that limit that we're going to be using pretty much for everything today is a limit as n approaches infinity of a sum from k equals 1 to n of f of x sub k times delta x. And as we talked about last time, our delta x value is always going to be equal to b minus a over n. Because remember, delta x is just the width of one of the rectangles that we're drawing underneath this curve. And so the width of one rectangle is the length of the entire interval. In this case, it's going to be b is going to be 2 and a is going to be 0. So 2 minus 0 divided by n. Right. So I'll actually write that out. This is 2 minus 0 over n for us, or just 2 over n for this particular interval. Now, what we're then going to have to do, though, is figure out what x sub k actually represents. And so we'll start this off by just writing out this integral here as this limit. So it's going to be a limit as n approaches infinity of a sum from k equals 1 to n of f of x sub k. Well, f of x is 3x, so f of x sub k will just be 3x sub k times delta x, which we just found to be 2 over n. And we now need to figure out what x sub k is. So the way we're going to do that is we're going to break this this region that we're talking about, this area that we're talking about, into some rectangles. And I'm going to draw them as, just to make the algebra a little simple here, we're going to draw them as right rectangular approximations. So I'm just going to draw a bunch of rectangles underneath here from 0 to 2. And it doesn't really matter how many of them I draw. But if I look at the first one of them, let's say this first little tiny interval down here, we have to ask ourselves, what is x sub k? Well, x sub k has to be the x value at which we draw the height of that rectangle, which is however far we've gone over from 0. Well, in that case, we'll talk about this as the first, k is 1, we'll talk about this as x sub 1. First x value that we've got here is just the length of one subinterval. And we know the length of one subinterval is 2 over n. Okay, so, well, that's x sub 1. But what about x sub 2? Well, x sub 2 is what we'd get if we go over 2 full subintervals, right? So x sub 2 is going to be 2 over n plus another 2 over n, or it's going to be 2 over n times 2. Well, if we're talking about x sub 3 is going to be this distance of 3 subintervals. Well, that's 3 2 over n. So x sub 3 is going to be 2 over n times 3. And as I go over any value of k subintervals, if I go over 4 subintervals or 7 subintervals or 1,000 subintervals, it's just going to be the length of one of them times 3 or times 7 or times 1,000. Right? So if I'm going over k subintervals, that means I'm going to have 2 over n times k as my x sub k value. Or just 2k over n. So now what we've got here is a limit as n approaches infinity of a sum from k equals 1 to n of 3x sub k, and x sub k we just said was 2k over n. So we have 3 2k over n's, and then we have 2 over n. And now all we have to do is evaluate this summation like we learned how to do a couple days ago. And then once we have that summation figured out, we'll evaluate the limit. So first we'll simplify down this limit as n approaches infinity of a sum from k equals 1 to n of, well, 3 times 2 times 2 is 12. So we've got 12k over n squared. And if we think about this, we should be able to see that that 12 over n squared is just some constant within the concept of this summation, right? N within this summation is just, it's just a number, right? We're going from k equals 1 to some arbitrary value of n. So if we think about it, 12 over n squared, this is just constant. And if we have a summation of constant times some variable, something changing, that k is changing within that summation, we can pull that constant out of it. So effectively, this could become a limit as n approaches infinity of 12 over n squared times the sum from k equals 1 to n of k. And very conveniently, we learned last time how to find the sum from k equals 1 to n of k. This thing right here, the sum from k equals 1 to n of k, that part right there is just n times n plus 1 over 2. So I can now rewrite this without the summation as a limit as n approaches infinity of 12 over n squared times n plus 1 over 2. And this should be a really easy limit for us to evaluate. First, we'll simplify it down. We'll note that it's a limit as n approaches infinity. Well, let's see here. 12 times n plus 1. That's going to be 12n squared plus 12n all over 2n squared. And if we plug in infinity this, we get infinity over infinity. And there's a bunch of different ways we can think about evaluating this. One is we could divide everything by the highest term. Another one is we could just go straight to L'Hopital's rule. Or we could just remember that, well, a limit as n approaches infinity of some function, some rational function here that's all in terms of n, is just looking for the horizontal asymptote to the right. So we can just divide the leading coefficients if the degrees are the same. So whatever way you look at it, let's just say we're going to use the rule for horizontal asymptotes. That says that if the degrees are the same, n squared and n squared, we can divide the leading coefficients. And 12 over 2 is 6, which tells us that the area underneath that curve that we started with, the curve y equals 3x from 0 to 2, is 6 units. And next time we're going to talk about the fact that we can do some of these integrals using geometry. And we'll probably note that that was just a triangular section. And we could have very clearly just said, well, the area is 1/2 of the base, which was 2, times the height, which was 6. And we could have really quickly and easily seen that that came out to be 6. But this does verify for us that this other method that we use with the limit summation really does work. The area underneath that to be 6. So let's do it with another one. Here we've got an integral from 1 to 4 of 4x dx. So I'm going to start by just writing it out as a limit as n approaches infinity of a sum from k equals 1 to n of f of x sub k times delta x. And again, as I said the last time, we know what delta x is, right? Delta x is just b minus a. So in this case, 4 minus 1 over n, or 3 over n. But this time, let's see if we can kind of figure out what x sub k is. We can just convert all that in one step here. So I'm talking about integral from 1, right here, over to 4, right here. Let's draw those right rectangles in here again. I'm just going to draw a couple of them in here. Again, it doesn't really matter how many you draw. I'm just going to draw 3 of them this time. And if I think about what that first x value is, x sub 1, how far did I have to go from the origin over here to get the height of that rectangle? Well, I had to go over whatever one interval was, 3 over n, but I also had to go over this space here at the beginning that's not part of my integral. I had to go over 1 unit. So x sub 1, that x value is 1 plus 3 over n. And if I think about the second one, I'm going to have to go over 3 over n twice, one for each of those subintervals. I got 2 subintervals now. But then, after that, I've also got to do that little 1 that I had at the beginning. So x sub 2 now going to be 1 plus 3 over n times 2. And we could see that x sub 3 is going to be that same 1 that we had to go over to begin with, plus 3 over n. X sub a then ought to be 1, our a value, plus 3 over n times k, or 3k over n. And we're going to note that this is slightly different than what we had the first problem, where x sub k, I'm going to go back to this here, x sub k was just 2k over n. Okay? We didn't have to add anything because our integral was starting at 0. But this time, since our integral is starting at 1, we've got to add that 1 in each time for x sub k. And we're going to, as we go through, we'll see that this is true. We're going to note that x sub k is always going to be equal to a plus k times delta x. Okay? And so since delta x is really easy to find, it should be really convenient for us to know this formula. We should really be able to come up with our delta x and our x sub k really quickly. Right? And we'll say delta x, as we said before, is b minus a over n. You're really going to want to remember those 2 rules in order to convert some of these integrals into a limit and a summation. Now, normally on the AP test, you're not going to have to convert it and then evaluate it, but I think it's good practice for us to evaluate them. But on the multiple choice, it's relatively common for you to see one where they ask you to just take an integral and put it into a limit and a summation. So we're going to work on that a little bit more today. So now we've got a limit as n approaches infinity of a sum from k equals 1 to n of 4x sub k. So 4 times 1 plus 3k over n, and then times delta x. And the delta x is just 3 over n. And it's a little bit messy, and most likely on the AP test, this is actually as far as you're going to need to go. But I'd like us to be able to evaluate this all the way to a final result here. So we'll do a limit as n approaches infinity of a sum from k equals 1 to n. And now I'm looking at a 4 and a 3 over n multiplied by this 1 plus 3k over n. So really, we're looking at 12 over n times 1 plus 3k over n, which will then give us a limit as n approaches infinity of a sum from k equals 1 to n. Well, 12 over n times 1 is just 12 over n. And 12 over n times 3k over n is going to be 36k over n squared. And so we're now ready to evaluate the summation. And we'll think back to what we did in the previous one, where we said that the value of n is just a constant. And if the value of n is just a constant, that means that 12 over n is just a constant. And what we did a couple days ago is we summed together a bunch of constants from the first one to the nth one. And we came up with a rule for that. It said if you're adding together a bunch of constants, okay, from the first to the nth, you just multiply the constant by n. So this can now become a limit as n approaches infinity of 12 over n times n plus, we said 36 over n squared was just constant. So we'll have 36 over n squared times the k value. When we sum k from 1 to n, that's n times n plus 1 over 2. And note that I don't have to, with that 36 over n squared right here, I don't have to multiply that by n, because I'm not adding together those constants. I'm just adding together a bunch of k's. That's the n times n plus 1 over 2. A bunch of k's that are being multiplied by 36 over n squared. So I don't have to worry about multiplying that constant by it. It's just constant within another summation. We should immediately be able to see that in the first part of this, the n over the n is going to cancel out. And then on the other side, we're going to have just a nice little rational function again. So we're going to have a limit as n approaches infinity of 12 plus, we had 36, so we had 36 times n plus 1. That would be 36n squared plus 36n. All over 2n squared. And well, this is a sum of two different functions, 12 and then this rational function. And if you're taking a limit of a sum of two functions, you just take each limit separately. The first limit, constant, the limit as n approaches infinity of 12 is just 12. And then 36n squared plus 36n over 2n squared is once again a rational function where the degree of the numerator and the degree of the denominator are the same. And so if we're going towards infinity, we can just use that rule that says divide the leading coefficients. 36 over 2 is 18. And this gives us a value of 30. And we might note that if we're talking about, I'm just going to quickly sketch this. It was y equals 4x from 1 to 4. We were talking about the area there. That's really just a trapezoid sitting on its side with a height of 3. And since this is 4x, this first base here is going to be 4. And this second base over here is going to be, well, 4 times 4 is 16. And so we could have just done base 1 plus base 2 divided by 2 times the height of 3, which would have, again, also given us 30. And so there's often a good geometric way to solve some of these fairly basic integrals. So here we've got an integral from 0 to 3 of 2x plus 2 dx, which I've got graphed here. And let's just quickly off to the side come up with our values for delta x. Delta x is just b minus a over n, or 3 over n. And x sub k is just a, which in this case is 0, plus k times delta x, or just 3k over n. So we've already got our delta x, and we've already got our x sub k. So we just throw this really quickly into our limit and our summation. A limit as n approaches infinity of a sum from k equals 1 to n of 2 times x sub k plus 2 times delta x. Same limit and summation we've been doing this whole time. And it just requires some simplification here. We've got a limit as n approaches infinity of the sum from k equals 1 to n. Well, this now is 6k over n plus 2 times 3 over n, which becomes that same limit and that same summation, except this time we'll distribute the 3 over n through, so that'll give us 18k over n squared plus 6 over n. And now this looks very similar to what we were dealing with in the last one. Can now become a limit as n approaches infinity of 18k over n squared will be 18 times the summation of k, which is n times n plus 1 over 2. And then we have to keep that over n squared that was in there. And then the 6 over n is again just a constant. So that's 6 over n times n. And now we do the same thing we did before. And I don't think we really need to expand out that numerator. We can see that the degree of that numerator is 2. It's going to be 18n squared in the numerator over the 2n squared in the denominator. Again, a rational function, so we'll divide the leading coefficients. That first part of it is 9, and the second part of it, when we divide the n's, just gives us 6, and we end up with 15. And once again, we won't go through the work for it this time, but from 0 to 3 of 2x plus 2, this area right here, that's again just a trapezoid. One base is 2, another base is 8, and the height is 3 going across the bottom. So we'd average the bases and then multiply by 3. And it'd come out to be 15. Now, we're going to do one more of these linear ones that could be done geometrically. But this one's going to be slightly different. We're going to note that this one, for the function 3 minus 2x from 2 to 4, actually has dropped us below the x-axis. And again, we can see it's a trapezoid. So we could use the formula for the area of a trapezoid to find that. But we're going to do it using the limit and the summation and see that this integral is actually going to come out to have a value that is negative. Anytime we have an integral, a definite integral of something that is below the x-axis, that value will come out to be negative. Anytime it's above the x-axis, that value is going to come out to be positive. And if you have an integral of something that's partially above and partially below, some of those areas are going to cancel each other out because the stuff above will come out as a positive and the stuff below will come out as a negative. And so you're not actually going to be getting a true area underneath the curve for those when you do the integral. So let's move through this here. We've got delta x is going to be equal to b minus a, 4 minus 2 over n, or just 2 over n. And x sub k ought to be my a value, which is 2, plus k times delta x. And we'll throw this into our limit and our summation. It's going to be a limit as n approaches infinity of a sum from k equals 1 to n of 3 minus 2 times x sub k, 2 plus 2k over n, times delta x, 2 over n. And so this one's going to get a little bit messier with the algebra, so just be careful with your algebra. We'll kind of take it in a couple steps here. First, we've got the negative 2 being multiplied by the 2, which is a negative 4. And I have the constant of 3, and then a minus 4. 3 minus 4 is going to give us negative 1. So we're going to have negative 1. And then we've got the minus 2 times the 2k over n, which is negative 4k over n. And that's still being multiplied by 2 over n. So we'll simplify that down a little further. We'll distribute that out. That's going to give us negative 2 over n minus 8k over n squared. And once again, this one is just the same idea. We're going to take that negative 2 over n and multiply by n because we're summing together n of them. And since we're summing together negative 8 over n squared k's, we'll just multiply negative 8 over n squared times the sum for k. So we've got a limit as n approaches infinity of negative 2n over n minus 8n times n plus 1 over 2. And then we still have that n squared. First one comes out to be negative 2. And that second one is another rational function, negative 8n squared minus 8n over the 2n squared. Divide the leading coefficients because the degree of the numerator and the denominator are the same. So we'll have negative 8 over 2 is negative 4. And had we gone through and we found the area of that trapezoid, we would have found that its area was 6. And we would have then needed to recognize that if we were evaluating for the integral, that's below the x-axis, we would have had to take that 6 and turn it into a negative 6. All right, we've got just a couple more here. Now, this time we're going to take a look at one that we don't have a nice, easy geometric way to do. We can't find the, we can find the area of a triangle, we can find the area of a trapezoid. It's pretty straightforward shapes, but for a parabola, there's no straightforward shape underneath it. We're just looking for whatever the area of this region here between 0 and 2 is. Nice little curved region on the top, horizontal and vertical on those sides there. But there's no formula specifically for that area. So what we'll do is we'll write out a limit and a summation. Delta x is going to be 2 minus 0 over n, so that's just going to be 2 over n. And x sub k is going to be 0 plus 2 over n times k, so that'll just be 2k over n. And we'll write that out as a limit as n approaches infinity of a sum from k equals 1 to n of 3 times x sub k squared times delta x. And we'll simplify that all out, hopefully just in one little step here. A limit as n approaches infinity of a sum from k equals 1 to n of, well, let's see here. We've got 2 squared is 4 times another 2 is 8 times the 3 is 24. And then we have a k squared up there. And then in the denominator, we've got an n that's squared times another n, so that's n cubed. And 24 over n cubed, just like previously, that's a constant, but it's being multiplied by k squared. And we know the summation for k squared. We did that little induction proof the other day. So we have a limit as n approaches infinity of 24. That's not 4. 24 times the sum for k squared, which is n times n plus 1 times 2n plus 1 over 6. And then we still have that n cubed in the denominator. And the nice thing about these is for these really simple polynomial functions that we're dealing with so far, these are always going to just turn into rational functions for these limits. And the rational functions are always going to end up with the same degree in the numerator and the denominator. In this case, that degree is going to be 3. If I were to distribute everything out there in the numerator and the denominator, or in the numerator at least, I've got an n times another n times another n. It's going to give me the same n cubed that I have in the denominator. So really, I just got to look at those coefficients. I got a 24 and a 2 is going to give me 48. So effectively, this is 48n cubed plus some other stuff over 6n cubed. I'll just divide the leading coefficients because the degree is the same. It's just 48 over 6, which is just 8. So the area underneath 3x squared from 0 to 2 is just 8 square units. We've got one last one that we're going to do here. And this one will note that a piece of this is above the x-axis and another piece of it is below the x-axis. So if we're looking at the integral from 1 to 2, here's 1 and here's 2, of 6 minus 2x squared, we've got a chunk of that that's above. This part of that integral is going to come out to be a positive value. And this other little part that's between that curve and the x-axis is going to come out to be a negative value. Those are going to cancel out a little bit. So it's not actually telling us the area of these two regions summed together. It's actually telling me the area of the region that's above minus the actual physical area that's below the x-axis. Between whatever that value there is, we can find that value over to 2. And so let's come up with our delta x. Let's come up with our x sub k and see if we can evaluate this integral. So delta x is going to be b minus a, in this case 2 minus 1 over n, or just 1 over n. And x sub k is going to be a plus k times delta x, so 1 plus k over n. And as we go through and put all this in, we've now got a limit as n approaches infinity of a sum from k equals 1 to n of 6 minus 2 times x sub k, which is 1 plus k over n squared, times 1 over n. And again, this one's going to get a little bit complicated with our distributing, so just be careful with this. Becomes a limit as n approaches infinity of a sum from k equals 1 to n of 6 minus, and I'm going to try and do this 1 plus k over n squared and multiplied by the negative 2 at the same time. So if I had, I'll write the 1 plus k over n squared. If I had 1 plus k over n squared, right, that's going to be the same as 1 plus k over n times 1 plus k over n, obviously. And the 1 times the 1 is just 1. If I multiply that by a negative 2, that's minus 2. And then I'm going to have the 1 times the k over n, the other 1 times the k over n, and another k over n is 2k over n. So I've got 2k over n there. But that's still being multiplied by this negative 2. So that ought to be a minus 4k over n. And then the k over n times the k over n, that part's just k squared over n squared, but I've got negative 2 of them, so minus 2 k squared over n squared. And that's still all being multiplied by 1 over n. All this, and just move forward with it. The 6 minus the 2 is going to be just a 4. And if I have 4 times 1 over n, that's going to be 4 over n. And then I've got negative 4k over n times 1 over n. That'll be minus 4k over n squared. And then the minus 2k squared over n squared times 1 over n will be minus 2k squared over n cubed. And so now just evaluate the summation. The limit as n approaches infinity of 4 over n times n, because that part's just a constant. And then minus 4 over n squared times the k, which is n times n plus 1 over 2. So 4 times n plus 1 over 2n squared. And then here we've got the minus 2, and then times the summation for k squared is n times n plus 1 times 2n plus 1 all over 6. And we still have the n cubed attached to that. And that limit just becomes 4n over n is 4. And then we have minus the 4n times the n is 4n squared over the 2n squared. So that's going to be minus 4 over 2, or minus 2. And then over here, we've got another minus. We've got 2 times n times 2n is 4n cubed over 6. So minus 4 over 6, or minus 2/3. And so we've got 4 minus 2, which is 2. 2 is 6/3. 6/3 minus 2/3 ought to just be 4/3. And that is the value of our integral there. And that's going to do it for what we're doing today. Next time, we're going to take a look at some other common integrals that you might want to go solve using geometry. And then from there, we're going to go into some proofs of how derivatives and integrals really work as inverses of each other, inverse operations of each other, and then get into some integral rules to make this process a whole lot easier. But that's it for today.